can you see the screen?
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
all right. So in the last class, I think we have covered up to reversible adiabatic process, isn't it?
Yes, sir. Yes, sir.
Yes, sir.
Okay. So we started with the calculation of PDV work in various quasi-static processes. Okay, these were the various various quasi-static processes. Constant volume process, we discussed that the work is equal to 0. If it is a constant pressure process, then the value of the work transfer is given by this relation. W1 to 2 is equal to PV2 minus V1, which is equal to MR T2 minus T1. Then we have discussed about the isothermal process, in which case the value of P into V is constant. And for this particular case, this is the derivation or the formula for the work transfer. W1 to 2 is P1 V1 log natural P1 by P2, and which is also equal to MRT1 log natural V2 by V1. So all these are the relationships for the constant temperature process. Now this is the reversible adiabatic process. I told you in a case of a reversible adiabatic process, there is no heat transfer, and when we calculate the work transfer value, the value is equal to W1 to 2 P2 V2 minus P1 V1 divided by 1 over 1 minus gamma, which can be written as P1 V1 minus P2 V2 over gamma minus 1. Okay. Now the next process is the polytropic process. Now this polytropic process is a different process, means it can be any process. You can convert this process into a isothermal process, constant volume process, constant pressure process, or any process which you can think of. And the relationship between pressure and volume is given by PV raised to power n is equal to constant, where n can have any value. Okay, so I have written it here. PV raised to power n is equal to constant in case of a polytropic process. N can have any value. So let us see, if we take different values of n, then which process we can get actually. For example, if the value of n is equal to 0, so what I have done here, I have put the value of n as 0 here. So this gives me P raised to power 0 becomes 1, and it gives me pressure is equal to constant. So it means when n is equal to 0, I get a process in which the pressure is equal to constant. Okay, so it's a constant pressure process. Now let us say if I take
So, sir, can't we say it is isobaric?
see, when I say constant pressure process, okay, what is your name?
Sir, Anshul.
Anshul. Are you known by the same name at your home as well as college?
Yes, sir.
You are Anshul at your home and Anshul at college also.
Yes, sir.
Your parents don't call you by some pet name at your home, like Anshu. Hmm? No, you don't have any other name. See, sometimes we have two names. So when I say constant pressure process, I have already told you it's a isobaric process also. Its another name is isopistic process. So it's a silly question actually.
Oh,
Now when I say n is equal to 1, okay, n is equal to 1, I can put the value of n equal to 1 here. Okay, so here I have put n is equal to 1. Now you see it here it is PV is equal to constant. For PV is equal to constant, it means from the gas equation, if you see, what is the gas equation? It is PV is equal to MRT. Okay, and I say that the T is constant. Okay, T is constant. So this whole right hand side, is constant. Okay, so it means PV is equal to constant means temperature is equal to constant. So you can see it here. This T is equal to C upon MR. Okay, MRT is constant. So this value is constant for a particular gas. So basically when n is equal to 1, it is a constant temperature process or isothermal process. So that means for n is equal to 1, it is temperature is equal to constant or it is isothermal process. So basically, I have given you the example in two cases where the value of n is equal to 0, where the value of n is equal to 1. But I will extend this for the remaining processes also. For the timing, I am going to calculate the work transfer for the polytropic process. So let us see. I just wanted to tell you that what is the polytropic process. Polytropic process can take the shape of any process. It could be isothermal process, it could be isobaric, it could be isochoric, it could be reversible adiabatic process. In case of reversible adiabatic process, N is equal to gamma. You know that PV ratio or gamma is equal to constant in case of reversible adiabatic process. So if when I have the process PV ratio or N is equal to constant, and if I replace N by gamma, it becomes the polytropic process will become a reversible adiabatic process. So if you see it here, I have once again started from delta W is equal to PdV, then integrating it between the states 1 to 2, considering that the process is taking place from 1 to 2. And I'm not going to discuss about how this integration has been done, because this has been explained already for the reversible adiabatic process. So you can see it here. In case of a reversible adiabatic process, the value of W1 to 2 was equal to P1 V1 minus P2 V2 divided by N gamma minus 1. So when it is a polytropic process where the relationship is PV raised to power gamma is equal to constant, I will get the value of W1 to 2 as P1 V1 minus P2 V2 divided by N minus 1. Then PV is equal to MRT. So P1 V1 is yeah, there is a mistake here, so it should be T1 minus T2. Okay, so MR T1 minus T2 divided by N minus 1. So this is the work transfer for the case of polytropic process. Is it clear? Any questions?
Sir, by this formula, like we can calculate work for every process except for isothermal process, right?
Yes, because in case of isothermal process, the denominator gives you 0.
Yeah.
Okay, for other cases, you can calculate use this particular equation. Okay. Now for constant volume process, what is the value of N? Now I am going to calculate the value of N for the constant volume process. I have told you it for the constant temperature as well as constant pressure process. Now let us see what is it the value of N for constant volume process. So you can see it here. When I take PV raised to power N is equal to constant, then I have taken the nth root for this particular equation for PV raised to power N is equal to constant. So when I take the nth root, you get this particular equation: P raised to power 1 by N, V raised to power N by N, C raised to power 1 by N. So you can see it here. It gives me P raised to power 1 by infinity. If I take N is equal to infinity, just see it. Just try to see it. P raised to power 1 by infinity, V raised to power. This has already become N and N cancels, and this is V raised to power 1 and C raised to power 1 by infinity. So we can consider the right hand side as constant, and P raised to power 1 by infinity becomes P raised to power 0. So it becomes V raised to power V is equal to constant actually. So that means for a constant volume process, the value of N will be equal to infinity. Okay, so it can have either the value of N as infinity or minus infinity. No, similarly, N is
P raised to power 1 by infinity भी 0 आ जाएगा ऐसे, तो मतलब P raised to power 0 that will be 1, so P is equals to 1 हो जाएगा.
Hello.
Yes, so
Sir, he's saying that C raised to the power 1 by infinity
1 by
tends
infinity
to 1.
power
So
0, that is 1.
volume will become 1.
Actually, we can have certain value for it, because if we will see, it cannot be 0 actually in this particular case also. It will once again a new constant.
Okay.
Whereas the value of P we have considered to be 0, 1 actually. Okay, but constant will have some, we have to consider some value of constant actually. Okay, because volume will not be 0. Volume will not be 0. Okay, so when we are proceeding for N is equal to infinity, yes, the pressure value will be constant. It's you can say that this term becomes 1, but volume can never be 0 in that particular case. Okay, so it will be, I will show it on the diagram also. There is another way of explaining it. I will tell you later on. Okay, so N is equal to infinity or minus infinity. Now if N is equal to minus gamma, then I have already told you that the process will become PV raised to power gamma is equal to constant. Okay, instead of N, I am putting gamma. So you know that gamma is equal to 5 by 3 for a monoatomic gas, and the value is 1.666. If it is a diatomic gas, the value is 7 by 5, it is 1.4. For example, this is very important. For air, you should always remember this particular value, or any other diatomic gas. If it is a polyatomic gas, the value is 1.333 or 4/3. This you have studied in your 11th standard also. Okay, now let us calculate the slope of any process on a PV diagram. So what I am trying to say is, for example, you have a PV diagram. You draw any line actually. For example, this line or this line or this line, and you want to calculate the slope of this particular process. So actually, any of these lines which I am representing here is representing a general process, and that general process is PV raised to power n is equal to constant. Okay, PV raised to power n is equal to constant. So we can differentiate this particular equation. So differentiation is already known to you. Okay, so what is the slope value? It is equal to dp by dv, and for dp by dv you can see the value comes out to be minus n p by v. Okay, so dp by dv is equal to minus n p by v. So this is the slope of any process on a PV diagram. For isothermal, you can consider any process actually. Okay, so this is the value of the slope. Dp by dv is equal to minus n p by v. Slope of a general process is, that means, minus n p by v. Let us show all the processes on PV diagram now. Now first case, I am considering a constant pressure process. When I say constant pressure process, and I have to calculate dp by dv. So I have written this particular equation. Now what is the value of dp? dp becomes 0 because pressure is constant. So the slope is 0. So that means, what is the value of n from here? If you will like to calculate the value of n, because this value is 0, so what is the value of n from this equation? The n will come out to be 0. Okay. Now let us take constant volume process, for which n is equal to plus minus infinity. Now you can see it here. Now when I am calculating the value of dp by dv, because v is 0, okay, so this comes out to be infinity, and this is equal to minus n. It is written here actually. So this value is equal to minus n p by v. So if I have to calculate the value of n, so you can see this value of n will come out to be minus infinity. So n is equal to infinity or minus infinity for the constant volume process. So you can see it here also. The slope is infinite actually. So it is representing the this process is also showing the slope of the constant volume process, which is infinite in this particular case. I hope this is clear. Now let us plot both constant volume and constant pressure process on same PV diagram. There is a particular reason why I am saying it. So constant volume and constant pressure. For a constant pressure process, this is constant pressure. The value of n is equal to 0. This is constant pressure, and this is constant volume, for which the value of n is equal to infinity. So basically you can see the value of n is varying from 0 to infinity in the clockwise direction. So I know that for a constant temperature process, n is equal to 1. So where it would be? It would lie somewhere here. Okay, it would lie somewhere here. So okay, so you can see it here. What I have written is PV is equal to constant and n is equal to 1. So I can say V is equal to C by P, or P is equal to C by V. So as V is increasing, P should go down. Okay, from this relationship you can see if the V increases, P should go down. Okay, it is clear. So that the value of P into V is constant, and P is equal P into V is equal to constant is nothing but a constant temperature process. Okay, so it also shows that when the volume is increasing, pressure should go down. So the process should take place in this particular direction from 1 to 2. Okay, so in next slide you will see it. So you can see it. I have shown all the processes here. N is equal to 0. This is a constant pressure process. When I take constant temperature process, n is equal to 1. Okay, and when I take n is equal to gamma, the value is either 1.67, 1.4 or 1.33. So you can see the polytropic process, reversible adiabatic process, has a steeper slope in comparison to constant temperature process. So dP by dV for PV raised to power gamma is equal to constant is greater than dP by dV for a constant temperature process. This is visible from here. Okay, and then this is the constant volume process in which the slope is equal to infinite. So this is how we can represent various processes. Now I will tell you one more thing. Here I have shown these processes. Okay, so if this is the first process starting from here, this is point number 1, this is point number 2, this is constant pressure process, this is constant volume process. For constant volume, point number 2 is here. Now this is temperature is equal to constant for it. This is the point number 2. This is constant reversible adiabatic process. This is point number 2 for that. Now you can extend this chart further also. Okay, you can go in this particular direction also. So it will be like this. So once again, now here this is PV raised to power gamma is equal to constant, and this is temperature is equal to constant. So the slope of the constant temperature process is lesser in comparison to the slope of reversible adiabatic process. So I hope this part is clear to you. So basically what I have discussed is I have calculated the value of work transfer W1 to 2 considering the system as the closed system. Okay, I will write all the equations here for your if it is a constant volume process, what is the value of W1 to 2? For constant volume, value is 0. If it is constant pressure process, the value of W1 to 2 is equal to P into V2 minus V1, which can also be written as MR T2 minus T1. If it is a constant temperature process, then the value of W is equal to P1 V1 log natural V2 by V1, which is also equal to MRT1 log natural P1 by P2. You can write it in 8 ways actually. When I say PV raised to power gamma is equal to constant, the value of work transfer is equal to P1 V1 minus P2 V2 divided by gamma minus 1. If I take PV raised to power n is equal to constant, then the value of W1 to 2 comes out to be P1 V1 minus P2 V2 divided by n minus 1. So these are the 5 relationship for the work transfer. Then we have calculated the value of n. The value of n is equal to 0 for a constant pressure process. It is equal to 1 for a constant temperature process. It is equal to gamma for a reversible adiabatic process. And this is n is equal to infinity for a constant volume process. Okay, so basically what I mean to say that every polytropic process in some way could be some other process actually. Okay, so a polytropic process is representing all the processes with different values of n. So that you should always remember in your mind that a polytropic process could be any process. Okay, now let us proceed to the next topic. Now I am going to discuss about point and path functions. See, till now we have calculated the work transfer. When the topic of work was discussed, I said I will be using delta W. I am using this delta. I am not writing dW. Okay, so there is a difference between the two, and this difference is because of the point and path functions. You have just seen that the work transfer in each of the processes is different. Okay, the work transfer in each of the processes is different. It is not depending upon the initial and the final states. For example, you have just seen, if I have started the process from point 1, if I go along this line, this is point 2, then this is the area which represents the work transfer for a constant pressure process. If I go for let us say constant temperature process, then this is the area under the curve which represents the work. So that means if this is point number 1 and this is point number 2, and if the point number 1, let us say, is at the same state in both the cases, whether it is a constant pressure or constant temperature process, but the point number 2 is different now. Okay, so area is different. So that means the work is not dependent upon the initial and the final states. Okay, so let us this is just a introduction for you. Now I will read what is the difference between these things actually. So path function and point function. Now work is a path function. As you have seen, in all cases we get different values of W1 to 2, even if P1 V1 and P2 V2 are same in each case. Okay, or same in each case. Okay, even then the value of work will be different. Actually, in case of constant pressure, P1 and P2 will not be same as in case of other cases. Okay, so it's not for true for every case, but in maximum many cases it can be true also. Okay, so if it is a constant volume process, then this area is 0. So W1 to 2 is 0. Constant pressure process, this is the area PV2 minus V1, and it is representing the work transfer. If I take a constant temperature process, then this is the area which is representing the work transfer, and it is given by P1 V1 log natural V2 by V1. Okay, so PV raised to power n, this is a general process. I can take this, then the work transfer is this value. If it is a adiabatic process, this is the value of the work transfer. So the area is different. So the important information that we get from here is work depends on path being followed. It is not a point function. Now, what is a point function? That I will tell you. So, but the important point is work depends upon the path being followed. The way, the direction means what is the area under that path? It is depending upon that. And once the path changes, the work will change. You go like this, the work will change. You go like this, the work will change. You go like this, work will change. You go like this, the work will change. But it is equal to the area under the curve. Okay, in any case, if I take this as the process which is taking place 1 to 2, okay, so it may have some PV relationship, but I know that this is the area under this curve which represents the work transfer. So this is the PDV work, and I have already told you that we are calculating this PDV work for a closed system, minded for a quasi-static process, for a reversible process. Always remember that. So work is a path function. It is not a point function. Now I will come to the point function. All properties are point functions. For example, P, T, V, etc. Pressure, volume, temperature, etc. All these are point functions. Properties do not depend upon path being followed. They only depend upon end states. For example, let us see if this is the state point 1 and this is the state point 2. So there are 3 paths. What are these 3 paths? One path is A. You go along A from 1 to 2. You go along B from 1 to 2. You go along C from 1 to 2. And now you calculate the value of change in temperature from 1 to 2. What is the answer? The answer is clear. It is T1 minus T2. So whether you go to state 2 via path A, B or C, the answer will be same, that dt will be equal to T1 minus T2. So what does it mean? It means the properties do not depend on the path being followed. They depend only on the end states of the process. That is, properties are perfect differentials or exact differentials. So all properties of perfect differentials or exact differentials. So what is the meaning of perfect or exact? If it is a perfect or exact differential, I am representing it by D, and then the property, for example dt, for example dp, for example dv. So D represents the exact or the perfect differential. The meaning is clear. When I will integrate this equation between 1 to 2, then I will get the value at the final state minus value at the initial state. value at the final state minus value at the initial state. So only this can happen in case of a property. So properties are point function. Okay, that is why we use D of the property. D represents perfect or exact differential. So all this I have already told you. Okay, DH. H is enthalpy. So for enthalpy also, enthalpy is also a property. So I can write it as H2 minus H1. If it is du, u is internal energy. So I can always write it as u2 minus u1. So u is a property. S stands for entropy. So it is equal to S2 minus S1. So this is how I can write it and so on. So any property you can represent by uh, DH, DP or DV, whatever is the property name actually. Now, work being path function depends on path being followed. We cannot write this. You can see it. I have written dw equal to one integration from 1 to 2. So what I have written here, I cannot write. So this cannot be written. That integral dw, I can't write dw from 1 to 2 and it is equal to w2 minus w1 because I cannot calculate the work at the endpoints because work is depending upon the path being followed. So I can't write it. So instead of d, we use delta. Rather, we use delta W, where delta represents imperfect or inexact differential. Okay, it is not exact differential or perfect differential. It is imperfect and inexact differential. That is why when we write delta W1 to 2, I cannot write W2 minus W1. So you can see here, I have written equal to with a cross sign here. Okay, I have cut it. So delta W is equal to, I will write this integration as W1 to 2 and the meaning is clear. The meaning says that work transfer for process 1 to 2. This is one way of representing the work transfer. Okay, one way of representing the work transfer. The other way could be W1 to 2. So I am writing it as W1 starting from point number 1 and ending at point number 2. So this will be once again work transfer for the process 1 to 2. Or I can also use this method W1 to 2. This is also one and the same thing. That is work transfer during the process 1 to 2. Now there are certain books which write D instead of delta with a cut mark over it. Okay. Uh, I think some students' mic is not muted, so please mute it. Okay. So I can also use this cut mark actually represents imperfect differential, imperfect or inexact differential. So it also shows that we are using delta. So you can use either delta or D with a cut mark over its head. So I can always write D W or delta W. They are one and the same thing. Now, if we calculate the value of cyclic integral of delta t, so what the value will be equal to? Cyclic integral means I am starting from point number 1, going to point number 2, and then once again coming back at point number 1. So I start the process from 1 via path A, I go up to point number 2, from 2, I via path B, I come to point number 1. So it becomes a cyclic integral because the system is completing one complete cycle actually. That means it is starting from point number 1 and ending at point number 2. So in this particular case, the value of cyclic integral of delta t will be equal to t1 minus t1 because we are starting from 1 and ending at 1 only. So the value comes out to be 0. Just a minute, wait for a minute. Okay, so I hope this is clear to you. So I can always write cyclic integral of dp will be equal to 0, or cyclic integral of any property will also be 0. You take any property, the value will be equal to 0. Now, let us discuss a little bit more about point and path functions. So I hope the question of point and path functions is clear to you. Here you can see this was the equation of the delta W, which is equal to PdV. So I can say that dV is equal to delta W divided by P. Now you see this particular equation. Now what is the left hand side? The left hand side is dV and the right hand side is delta W by P. So this is a perfect differential. This is a perfect differential. Whereas this delta W is imperfect differential. Okay. Now how we can relate with them? So what I can write in next line is just try to understand. dV is a property. V is a property. I can, when I will be integrating it, I will be getting, see if I integrate dV from 1 to 2, I know that I will be getting V2 minus V1. But the right hand side is a imperfect differential. Then how I am getting this value of dV equal to V2 minus V1 from delta W? Okay, that is the question. See, the delta W is converted into a perfect differential by multiplying by a integrating factor, and this integrating factor is 1 by P. Okay, so that means when I multiply delta W, which is an imperfect differential, by the integrating factor, which is 1 by P, then on integrating this value from 1 to 2, I will get the value V1 minus V2 minus V1. So by multiplying delta W by integrating factor, we can get a point function, that is dV. So we have converted a path function into a point function by multiplying with a integrating factor that you should remember. So this is what I have shown here. So V2 minus V1 is equal to delta W by P for the process 1 to 2. Now the first work which we discussed was PDV work. We calculated the PDV work for a closed system. You should always remember that PDV we calculated for closed system. We calculated it for a reversible process, which is also called quasi-static process. Okay, and then the third validity condition for PDV was resistance at boundary. So if there is no resistance at boundary, it won't be a, we cannot calculate the PDV work. PDV work will be 0 and the process will be that of a free expansion. Okay. Now there is another type of the work which is known as the shaft work. So I hope all of you understand the term shaft. Shaft is basically a cylindrical section which is rotating part. Like if you have you must have seen a fan motor. So there is a shaft which is coming out from the fan motor, and that shaft is actually rotating. The blades are mounted on that shaft. When the shaft rotates, the blades of the fan also rotate. Or you must have seen some other things. Normally, if you have a washing machine, the rotor of a washing machine is mounted on a shaft. So shaft is something which is rotating, which is a cylindrical section basically. Okay, normally the shaft will be a cylindrical section in most of the cases. So we are calculating the shaft work in that particular case. So you can see here I have drawn this particular diagram here. So this is the shaft. This part is the shaft. This is cylindrical. If I will see the side view, I can see it is circular in shape. So what I am doing, I am trying to apply the torque over it. Okay, torque over it, and it gains a particular constant RPM or speed, and is the speed of the shaft. Okay, when a shaft is taken as a system, is rotated by a motor. Okay, there is a work transfer. So this shaft is rotating because of the motor, or it is not necessary that you have to rotate it by motor. You can rotate it by some other means also. Okay, this is one of the ways of rotating it. So what is happening? There is a work transfer into the system. Okay, this is because the shaft can rotate with a pulley which can raise the weight also. Okay, we defined weight, we defined work. Work is raising of a weight. Okay, so now we would like to calculate what is the work transfer when shaft is rotating. We are applying a torque over the shaft T, and suppose there is a rotation of this shaft. Okay, the rotation of the shaft is d theta. Let us say this is the initial condition. Then on rotation, it moves by angle d theta. So what is the value of the work? It is equal to T into d theta, and d theta is nothing but angular displacement of the shaft. And if it is rotating at a particular RPM, I can to calculate the total work transfer, whatever is the total motion of the shaft, total angular displacement of the shaft, I can multiply that by torque, and then I will get the value of the work. So T into d theta, integral from 1 to 2 will give me the shaft work. So this is the equation. The second could be, now this is work. When I am calculating the shaft work, the value comes out to be in Newton meter. Okay, Newton meter, because the torque is actually it is displacement into it is force into displacement. Okay, force into displacement. So Newton meter. So unit of torque is Newton meter. So Newton meter into d theta. D theta has the units of radians per second, radians rather. So Newton meter. So torque the value of torque is Newton meter, and the SI unit is either Newton meter, which is actually joules. So shaft power. If I have to calculate the power which we are inputting, then we have to divide this shaft work by time actually. So now I am putting a dot over its head. When I am putting a dot over the head of the W, it becomes the power. So whenever you see a quantity and there is a dot over its head, then it becomes a quantity which is time dependent. Okay, so T into d theta by d tau, and if I calculate this value d theta by d tau, it is nothing but omega. The value of torque is constant, it has been taken out of the integration sign, and this d theta by d tau can be regarded as the angular velocity. So angular velocity can also be given as 2 pi n divided by 60 radians per second. The third one, this is also important, pedal work or stirring work. Now let us see it. Now, what is a pedal work or a stirring work? Now see the system carefully here. What I have considered is, I have considered a container here. It is a container here. I can say it's a rigid container. When I say rigid, it means the volume is equal to constant. So in this particular case, the container is rigid and it is insulated also. So there is no heat loss from this container. That means no heat will be entering from outside to inside, and from inside to outside it will not be going, it won't be transferring any heat. So no heat transfer. And what I have done, there is a gas inside it. You can see there is a gas. Okay, and this gas is actually the system. This is the boundary actually. This is boundary. So wherever you will see the dotted lines, that is the boundary of the system, and that defines the scope of the thermodynamic system. So in this particular case, the thermodynamic system is only the gas and not the container actually. Okay, so what next we have done is, we have a, you can say there is a, this is a sort of pulley actually. You can consider this as a pulley. Okay, and a rope is wound over it, and this pulley has a shaft which is going inside this container at and at the end there is a, you can say a sort of rotor or a fan is installed, or you can also call this as a stirrer. Okay, which has a blades basically. So when this pulley will be moving, the shaft will move and the stirrer will also move in the gas. So what exactly we are doing, this is the rope here. Okay, at the end of the rope there is a weight. this is the weight. The value is equal to mg, and it is represented by w dash, because work we are representing by w. So w dash we are representing as weight, which is equal to m into g. And if you see from the center line of the shaft, initial position of this weight is z1. From here to here, initial position is z1. Now what we are doing, we are lowering this weight. This weight is moving downwards, and the final position is z2. So we say that it has been lowered by a value e, which is equal to z. Now this z is nothing but it is equal to z2 minus z1. Okay, so the weight is lowered by a displacement or a height which is equal to z actually. Now when this weight will be lowered, what will happen to the pulley? The rope will rotate the pulley, and when the rope will rotate the pulley, the shaft will rotate and the stirrer will rotate. So actually, when the stirrer will rotate, this is a sort of which is work which we are doing on the gas. So W, or the work is done on the gas. Okay. Now what will happen when there will be work on the gas which is there inside the container? So you can see, will there be any change in the volume of this container? I have already told it is equal to V is equal to constant. So there is no change in the volume. When there is no change in the volume, dV is equal to 0. So what will be the value of the work, PdV work? What is PdV work equal to?
0.
It is equal to 0.
0.
So there is no work. So whatever
0.
the work which we are inputting into the system, where will that go?
Internal energy will change.
Internal energy will change. Okay, its internal energy will increase, its temperature will increase, because we have already said that the container is insulated basically. Okay, so as the weight is lowered, the paddle wheel, it is also known as paddle wheel, turns. The work is transferred into the fluid system, which is a gas here. As the weight is lowered, the paddle wheel turns. There is work transfer into the fluid system, which gets stirred. The volume dV is equal to 0. So integral PD will be 0. That is, PdV work is 0. If weight W is lowered through a distance dz, here what I have shown, that the total lowering of the weight is equal to z. If I consider a very small displacement of this weight, which is equivalent to, let us say, dz only. Okay, so I would be able to calculate how much work is done on the system actually. Okay, so let us see it here. And torque T is transmitted by the shaft in rotating through an angle d theta. Okay, read it once again. If W dash, which is equal to m into g, is lowered through a distance dz, and torque T is transmitted by the shaft in rotating through an angle d theta, then what is the value of the delta W? Now this delta W is work. It is equal to T into d theta, and this will be equal to m into g into dz, which is basically the decrease in the potential energy. Okay, so I can integrate this equation. Delta W is equal to T into d theta is equal to mg dz, and W is equal to mg dz, which is equal to mg z2 minus z1, which is equal to, because this mg is equal to W dash, and this can be written as W dash into z, and this is also equal to torque which is being transmitted during this process from 1 to 2, and it is equal to T into omega. Once again, it is same thing, but mind it, this is paddle wheel work or stirring work, and this delta W is delta W which we have calculated here. It is this small work, and this is not PdV work. So don't confuse yourself. You should not be confused with that PdV work which we have calculated earlier and this paddle wheel work. So this is a different kind of work. Okay, so these are different kinds of the work which we are studying actually now. So we have till now discussed about PdV work, we have discussed about the shaft work, we have discussed about the paddle wheel work or the stirring work. Now the next type is the fourth number. It is known as the flow work. Now, what is this flow work? How it is different actually? So let us see it here. What we have considered here is the name is flow work. Now suppose we have a open system now. Now we are talking about a open system. Now in case of open system, naturally there is some fluid which may be moving into the control volume. I said in case of open system, we define a term which is control volume, and the surface of this control volume is known as control surface. The volume is inside, and this is the surface actually. Okay, so this is the control surface and control volume concept. So we know in case of a flow system, certain amount of the fluid is always going into the system actually, and certain amount of the mass is going out of the system. Okay, so let us first of all read what is given here in the slide. The flow work is significant only in a flow process or an open system. It represents the energy transferred across the system boundary as a result of energy imparted to the fluid by a pump, blower, or compressor to make the fluid flow across the control volume. So the definition is quite important actually. So you can read it once again. Flow work happens in case of a open system. It represents the energy transferred across the system boundary. Now this system boundary is nothing but the control volume only, or the control surface, as a result of energy imparted to the fluid by a pump, blower, or compressor to make the fluid flow across the control volume. So we are supplying the energy. For example, all of you must be having a motor, water motor, which you call as a pump also. Okay, for lifting the water from the ground level to the top level in your building or in your house actually. So that pump is nothing but, if I represent by this symbol, this is a pump actually. So you know that there is some inlet, there is some outlet. So from the inlet the water is entering into the pump, then the pump is increasing its pressure and lifting it to a particular height actually. So it's an open system. So we talk about the flow work in this particular case, and for lifting this water we have to supply certain amount of the energy, which is in the form of the electrical energy, which is also work in this particular case. So when we are taking the help of the work and making the fluid to flow, then we will have to do the flow work actually. Now flow work is analogous to the displacement work. Let P be the fluid pressure in the plane imaginary piston which acts in the direction normal to it. So let us try to see the diagram here. I think I will show you in the next slide. You can see this particular slide here. So you can see I have considered this volume actually, rather this this volume which is shown here. Okay, this is, you can say, a imaginary piston. Okay, this is an imaginary piston. Just wait for a minute. So this is a imaginary piston here. Okay, and there is certainly some fluid which is exerting, which is inside the control volume here. This is the control volume, and the fluid is inside this system also. So it is exerting a pressure P1 here. So if M1 mass of the fluid wants to enter into this, it have to overcome this pressure P1 to go into the control volume actually. So what we are showing here, this is the volume dV, which is trying to enter into the control volume, but it is opposed by this pressure P1 actually. So naturally we have to do certain amount of the work, or the fluid has to do certain amount of the work to enter into the control volume, and this work will be known as the flow work, and this is nothing but the PDV work only. So you can see it here. I have written here this is delta W flow. Okay, so if the pressure which is acting here is P1 or say P, so the flow work at the entry will be equal to P into dV. dV is the volume of the fluid which is trying to enter into the control volume. Or what I can do is I can also write this equation in other way. Now I am writing it as P into V. This V is specific volume. This is specific volume. Okay, and the unit is meter cubes per kg. And if dm is the small mass which is trying to enter into the control volume, then this total quantity V into dm is dV actually. So this is the same term, dV is equal to V into dm. Therefore, work at inlet, if I am calculating the flow work at the inlet, that value will be equal to P1 into V1 into dm1, where dm1 is the work which is trying to enter into the control volume. So delta W flow in, I can integrate this equation. It is equal to P1 V1 dm1. So what is the value of the flow work at inlet? This equation gives us the flow work at inlet is equal to P1 into V1, this capital V1 now. Okay, or if I want to calculate the flow work per unit mass, then it is equal to P into V, where I have once dividing by mass, it becomes specific volume. The unit is this. So flow work is P into V. So like when the fluid wants to enter into the control volume, it has to do the flow work. Similarly, there will be certainly some pressure which is acting at the exit also. So when the fluid will try to move out, then also we have to do certain amount of the work which is given by P2 into V2. So flow work is the displacement work done at the moving system boundary. Moving means flow system boundary. Okay, so this is the concept of the flow work. This is very important. So now it is 1. So I will stop my lecture here. Just wait for 1 minute. I will send you the link of the video also.